So now we will generalize what we've seen to a system of particles. So here you see a system of particles, and this is particle I, this is particle j, and you have lots of other particles. So the position vector of particle I is simply notated like this, right? So we will see that on each particle, and let's say I, of course there are different forces that are working on it. There are external forces, okay, and we'll say that the sum of all external forces acting on particle I will denote Fi. And similarly, there will be external forces acting on particle j. Okay, we'll call these Fj. But also there are forces that are internal to the system. For instance, if we draw the line between particle I and j, there is the force from j on particle I, and we'll call that one ji, right? But of course on particle I there are lots of other forces acting, like this one, etc. All the forces that I have drawn here are internal forces, and on each particle we'll assume that we can collect all in external forces and collect them in one term that denotes the external influences. Okay, as I've said before, the idea is the generalization to many particles. We talked about external forces. Okay, so on particle I there is a net force Fi, and there are internal forces. Okay, all particles, of course, except I, exert a force on I, and we've called that force Fji, right? Then for one particle we can write Newton's second law. Mass times acceleration vector is sum of the forces, and as I just said, there are external forces, one, and there is a collection of internal forces that are linked to all the other particles different from j. So you obtain this equation, right? And going from here to here, what we do is that now we sum over all particles I. Okay, this is for just one particle, and now we sum over all particles. This is why you have also an index I over here, an index I over here, and an index I over here. So we have this thing here is equal to the sum of the individual masses times their respective acceleration vector. Okay, so this one we can write a little bit differently by saying, well, we'll take I not only different from j but smaller than j. So okay, so of course you have this term coming from here, but then comes into play, if you write things like that, the other force Fij, right? It's kind of obvious why we do that, because we know by Newton's third law that this term here will cancel out. Remember, weak law of action and reaction. So what do we have? The sum of the external forces, forces on each individual particles, and this one we'll simply call it F, and this is then the net force, is equal to this thing here. this is a kind of nice result. We've just come up with this result, and if we define the center of mass, we can rewrite this equation to a form that is well known to you. So how do we define the center of mass? Okay, or the position vector of the center of mass, you simply write it like this. Okay, and the idea is that the center of mass is kind of the average position of all particles, and it's weighted according to their masses, right? So if you take this equation here and you put double dot here, this is the term that you have got here, well, and you take just that thing here, you can say that this thing, take the m, take it on the other side, is m, and then the acceleration vector of the center of mass, and this is equal to something like that. So it's just another notation, right? So this is second law of Newton, written for a system of particles, and you can see you can write it exactly in the same way, but you need this notion of center of mass. Here we've done, or we found, or defined this notion of center of mass for a system with many particles. Suppose that you have a rigid body, which says that you have kind of an infinite amount of particles. Things are dense. Well, then you have a similar formula for the center of mass that can be computed from an integral over a volume. Okay, and of course it involves the density. You have done things like that in other courses, in previous courses, so I won't go into the details of that. Remember that we have spoken about the definition of the center of mass, which is kind of the average position of all particles weighted over their mass. And we have seen that you can write second law of Newton. So the net force is equal to m times the acceleration vector of the center of mass. And very often, if not always, I will write things like that, so I will forget about this subscript cm. Okay, but if you're working with a system of particles, or if you're working with a rigid body, you have to keep in mind that you have to work with this idea of center of mass. Okay, so we arrive at a description of a system in translation. It's kind of obvious if you have a system of particles that you also have to do something about rotation, right? This is tackled in the next slides. So here you have a summary. This is the definition for a system of masses of the center of mass, and then you obtain a second Newton's law written, okay, where you don't have to forget that in fact you're having a subscript cm over here. Yeah, so the idea is that the center of mass of the system moves just as if it were a single particle of mass m, where m is the sum of all masses, and that it is subjected to an external force that is the sum of all forces that are influencing all particles, right? And this is the justification for treating extended objects as point particles, as we very often do. Okay, we'll now look how things are going when we consider the total system with my particles, in rotation. Remember my system of particles. I have particle I over here, j, the position vector of particle I, position vector of particle j, and what I will be needing is the difference Ri minus Rj, right? How can you see this? This is correct, Ri. If I then draw minus Rj, I have something like that, and this is my Rij. Okay, since it's a vector, I can just put it over here, right? So let us now look at the total angular momentum, which is the sum of each individual angular momentum. Remember that the angular momentum is a cross product of the position vector and the linear momentum. Okay, so we obtain something like that, and we remember that all position vectors are measured from the same origin O, right? So we're interested in the same law that we have derived before, but for a single particle. So this means that we'll take the derivative of the total angular momentum. This is what we do here, right? Again, two terms. The first one where we take the derivative of this one with respect to time. So this will involve the velocity vector of particle I, and this one here is the linear momentum of particle I. And since you have the cross product of the same vector, you can see directly that this is going to be 0, right? And then you have the sum, cross product of the position vector times the derivative of this one, okay? And this produces the acceleration vector of particle I. So we are now right here, right? This is equal to the time derivative of the total angular momentum. So what you see here is Newton's second law applied to one particle I. Okay, this is something that we've used before. Mass times acceleration vector. This is the sum of the external forces acting on particle I, and here is the sum of all internal forces, right? This is something we've seen in a previous slide, and you see that we have the same quantity over here. So what we'll do is inject this thing here in this formula. So we have the time derivative of the total angular momentum is equal to, well, a sum, right? And then we have a cross product of this one times this one. This is this term here, okay? And then you have a sum of this position vector cross product with this sum over here. This can be written as a sum over two indices I and j, and we remember that I cannot be the same than j because it's external forces coming from other particles than I. Okay, so here we have just copied the first term, and we're going to use that same trick that we've used before. Here we have a sum on ij, I different from j, but now we are going to do a sum on ij and I smaller than j. Okay, so it means over here that a fji will become a fij. Okay, so which means that you'll have a minus sign arriving here. And this thing we've just shown in the previous drawing, that we can write it as Rij. Okay, so this is the drawing that you saw on some previous slide. Remember that we are computing L dot, so the derivative of the total angular momentum, and we saw that in one of the formulas that we obtained where was a sum, and it involved Rij cross product with Fji. In most applications we'll see that the force Fji is what is called a central force. Well, this means that it is acting on the line that joins particle I and particle j. And if it is a central force, this means that the angle between Fji and Rij is 0. So all these terms here are 0. We had obtained this formula for the derivative of the total angular momentum, and we have seen in the previous slide that if the forces that are involved here are central, well, we can neglect this term here. Okay, and in most applications, for most familiar physical forces, this term will be 0. Okay, so what do we obtain? Well, we see that the time derivative of the total angular momentum is a sum of the torques that are acting on each individual particle I. Okay, and instead of working with this sum of torques, we'll work with tau here, which is the net torque that is applied to this system of particles, right? And again, if this net torque is 0, then we speak of conservation of total angular momentum. Okay, so let's make a summary so far. We are working with a system with several particles, and we have seen that we had that the variation of the linear momentum is the force or the net force that is being applied. So we have a generalization for this for a system of particles. We have now just seen that, so this is an equation in translation, right? And we have now just seen that you have a similar equation in rotation, and it's often called the rotational form of the second law of Newton, which says that the variation of the total angular momentum is equal to the net torque that is applied. Okay, we have derived this under the assumption that we are working in an inertial frame, as we've seen previously. If you are working in an inertial frame, then you can invoke Newton's second law. Remember that we've invoked Newton's second law several times in the previous slides. A word of caution: L, so the total angular moment, and the net torque, they are measured around an origin which is fixed in some inertial frame. Okay, and the remarkable thing that we'll see next is that we can extend this result here even if the L and the total angular momentum, I should say, and the net torque are measured around the center of mass. It has to be the center of mass then, even if the center of mass is being accelerated and is not fixed in an inertial frame. Okay, so in the next slides I will be working not with this position vector for particle I, but I will write this position vector Ri as the sum of the position vector of the center of mass plus some other vector that I will be calling Ri prime. Okay, and these vectors here have some properties that I want to show. So I'm starting from the definition of the center of mass. Remember that the position vector of the center of mass is this here divided by m. You can see it as the average position of each particle, averaged over each particle and weighted by the mass, right? So if I inject this one in here in the formula, this is what you obtain. So distribute things, and then I'll obtain this term here. This I can take up front, and then I can write it like that. You have this term here equal to this term here. Okay, I can simplify, and this means that this thing here is equal to 0. I will be using that later on in the slides. We had shown previously that the total angular momentum L can be written as the sum of all torques that are acting, net torques that are acting on each individual particle, right? So this is the linear momentum that you can write just like that. So again, I will replace the vector Ri, which is the position vector of particle I, and I will write it as RCM, which is the vector of the center of mass, and the position vector of the center of mass, and some vector Ri prime from the center of mass to particle I. This is what I've shown in one of the previous drawings, right? If I can write this for position, I can do something very similar for velocity vectors, right? So I'm going to inject this one over here, and I'm going to inject this one over there, and this is what I am obtaining, right? So you can rewrite it slightly differently in order to make the following sum appearing twice, and in the previous slide I've shown that this is equal to 0, this is equal to 0, so the two last terms here, they simply disappear. Okay, so we're writing the total angular momentum. We have rewritten it using these vectors Ri prime that are starting from the position of the center of mass to the individual particle I, right? We had initially 4 terms, but the 2 last terms disappeared. Yeah. Now we can give an interpretation of this. So this is the total angular momentum around the origin omega, and it has 2 terms. The first term is the angular momentum of the center of mass relative to the origin of your reference frame, right? The second term over here, this is simply the angular momentum of the system now relative to the center of mass. And this result is general in the sense that you can use it for a system of particles, individual masses, but it can also be used for continuous distributions, solid bodies, rigid bodies. Okay, this is the equation that we had obtained for the total angular momentum, but now we'll take a particular reference frame where the center of mass is fixed with respect to the origin. Okay, so let's make a drawing of that. remember our system with lots of particles, yeah, and then we had somewhere here the position of the center of mass, and we'll just say that this corresponds to the origin of our reference frame, right? Remember that previously we had written Ri. It is the position vector of the center of mass plus Ri prime, right? Well, since the origin and the center of mass coincides, this means that this is equal to 0, right? So this means that if this is, for instance, particle I, this vector is Ri. In this case, it's also equal to Ri prime. Okay? So, this term disappears, okay, because of this, and in this term you can replace Ri prime by Ri, and you obtain this expression here for the total angular momentum. Okay, remember that this is true for a reference frame. It will not in general be inertial. It's a reference frame attached to the system and centered in the center of mass. Okay, and if you do that, you still have the relation that is shown there.